Lars-Åke Fredlund presenting controlled scheduling of concurrent Elixir programs. Thank you.
Okay, thank you. So this doesn't work with... it's good that you applaud before, because afterwards you're not going to applaud. So it's good to get it before. So this is joint work with quite a lot of colleagues from UPM. But really, I was thinking how to present this, and well, maybe it's a better idea to try to also present the reason why we have worked with this control scheduling. And the reason is we're really interested in checking atomic Erlang Elixir APIs in a good way. Okay? So let's start with a motivating example. So here is a really simple API for working with mutable arrays. Okay, so there is an operation, a function for creating an array of size n. We can write a value at a position in the array. Notice that the write operation doesn't return anything, so it's really mutable, right? And lastly, there is just one way of observing the contents of the array. This is the scan operation that returns the contents of the array as a list. Okay, cool. This is a snapshot API. There are a lot of algorithms around snapshots. We are going to see a few of them. So the interesting thing is that this is intended to be a concurrent API, right? So writes to the array can be concurrent with scans from the array. There can be multiple scans, etc. So there is a whole lot of different restrictions one can put on this level of concurrency permitted, but we're not going to speak more about that. But think of it as a concurrent API, okay? So what is a really trivial, simple implementation of this one? Well, we can take almost any key value store. Perhaps ets tables is a good choice to implement this API. Okay, so we just assume we have two operations. We have an operation put for writing value under a key, okay, and we have an operation get that returns the value associated with the key, or nil, because this is Elixir. I'm sorry for that. If it doesn't exist, okay? And we use that in the implementation, so we have a create that does really nothing except calling kvnew. We have write, so this looks a little bit strange. Well, we put a new key in the table, but we are going to be, this first protocol just uses one array, which you call A, but a later version will use a different array, B, and maybe more. So that's why we use as a key the name of the array coupled with the index, okay? And scan operation is simple as well. We just do a map over the indexes in the array, and then for each index we get the value inside the key value store using get. Okay, so very trivial. Okay, trivial implementation, right? Nothing more to it. So here is one possible execution of this really trivial API. So suppose that we first call create, okay, and then next a process queue starts calling scan, and in this execution that we're interested in eventually returns the list nil20, okay? Concurrently with the scan, another process P first calls write 010. This is writing 10 to the first position in the array. And then write 120, which writes 20 to the second position in the array. So after all the operations have completed, the array should contain 10 and 20, right? Okay? So one possible execution result, the one I was speaking about, is the following, which we can depict as a time diagram where create operation always runs first. We have to create the array before doing anything else. And then we start the scan, which eventually, it starts at timestamp T1, and at timestamp T5 returns the list nil20, okay? And while the scan is ongoing, we call write 010, okay, and that terminates, and then afterwards we call write 120, okay? So this is one execution, possible execution of the implementation we saw on the previous slide, okay? So if you have any questions, just do it. Don't have to wait for answer session, okay? So the question we should ask ourselves is the above execution correct? Is it sensible, okay? So what does this really mean, right? We have a concurrent API. what is a correct execution? So intuitively, the scan operation should, of course, return a snapshot, a picture of the array at some point in time when it was executing. Okay? I don't know if that gives us any insight, but there is some classical ideas in this field. So from the 1990s, one idea was to define correctness of at least some of these concurrent APIs by stating that they should be linearizable, or I will also use the atomic sense of that. Okay, what does it mean? It means that if we have a concurrent execution, so here we have a concurrent execution, can we take these 4 calls and linearize them, execute them in some sequential order, okay? And when we observe the results, well, there's just one result. There's only scan that does return something. When we observe the results of this linear execution, it should coincide with the concurrent execution. So there can be many ways of giving a linear order of these calls, right? But there should be at least one that can explain the behavior of the concurrent execution, being identical. Okay? So I'm simplifying a little bit for those that know more about this stuff, but this is a simple idea. Okay? So let's look at this example, right? So we have this execution. The only thing that's really interesting is that the scan returns nil 20. So what are the linear orderings of this execution? Well, there are 3. Okay, so we have the first one. Create always begins. Okay, so we are going to respect the timestamps. If we know that one call executed and terminated before another call, it's always going to be before that other call in the ordering. Okay, so create always comes first because it's executed first, and then we have an option. Maybe the scan operation was run first. So the first one, we have scan here, scan 2. Well, that's cool. And then we have the write operation to the 0 position and the first position. And our alternative is that the write to the 0 position occurred first, and then the scan. And the third alternative is that the second write occurred before the scan as well. So we have to check if any of these executions can produce the result that scan returns nil 20. Okay? So that's our task. So we can check it manually, just let's do one. So what happens if we execute the first ordering? So creates the array, that's fine. Scan 2, what does it return in this case? We haven't written anything, right? So it just returns nil nil. It's not a good explanation of the concurrent execution. It doesn't work. Okay? It fails completely. The second one, well, we write 0 10 first. Well, and then we do a scan. Well, what will the scan return? It returns the first position has 10, the second one nil still. So it's not a good explanation because we return nil 20 there. No, it doesn't work. And likewise, the third one also fails because we are going to return 10 20. So there is no way we can linearize these operations, these calls, and explain the behavior of the concurrent execution. So if we take as given that we want the snapshot API to be linearizable, this naive implementation doesn't do. Okay? It's buggy. So what we have done, and this is not really the aim of this talk, or this paper at least, but a separate thing that hasn't been published yet. We're in the process of publishing, that's why I'm speaking about it. We have a tool, Stateful, for checking such linearizations of APIs, and the aim is to integrate it in the Corsa runtime code contract checking tool that we have developed as well. Okay? So the basic idea is very simple. So we are going to run a linearization monitor process, if you will, separate. And when we execute functions in this API that we want to check, these functions should inform the process, checking linearization, that the call has started with the parameters, the timestamp is very important. And when it terminates, the call as well communicates the return value and a timestamp when it terminates. Okay? And the monitoring process then goes about and checks whether there is any linearization that can explain this concurrent behavior. Okay? And why are we using Elixir? Well, for doing these instrumentations, it's really convenient sometimes to use the Elixir macro facility. So that's one excuse at least. I'm sorry for doing this in the Erlang workshop. And very important, so this is not really very new work. Okay, so we have an expert in the room, John Hughes, that has been doing this for a long time, using the quick-check EQC statum library. Okay, so he knows all about this. So all the questions will go to him. No, I'm just joking. So what is new? Well, this is a little bit different take on this. So if you work with the EQC state library, you're also concerned with how to generate test cases, right? That should be for checking the API. Here we don't care about generating test cases. We just have a monitor that monitors calls made to the API, okay? So it's a little bit different problem. It's a sub-problem of what they solve, okay? And because of that, we have a little bit different concerns with efficiency and things like that, okay? But that's a different topic. Okay, so we have that. So we have a bad algorithm, the naive algorithm. Let's look at a better algorithm. So there's a researcher, Gianti, that has developed a series of these snapshot algorithms for different restrictions on how much concurrency to permit. So we're going to look at one here. We don't have to understand this code. I probably don't do it also. It's more complicated for sure. Apart from this array that we write to, the snapshot array, this algorithm also uses a second array, a B array, and the idea is to somehow recover writes made by the write function that were lost during the scanning process. Okay? So giving a second opportunity, if you will. So one can point out some details, for instance. So the scan process, the first line, it sort of uses, it sets an X variable to true. This is indicating the scanning begins. And the write function, what does it do? It sort of first writes to the A array, as before, and then it checks whether X is true, whether scanning is in process, and then it will go on to write to the B array as well. Okay? And the scan process, after doing the normal scanning of A, also scans the B array, and if there are values there, well, then they will supersede the values on the A array. So more or less, that's the idea, right? So it's supposed to be a good algorithm with some certain limitations on the concurrency allowed. It's a very sensitive piece of code, so that if we change things around, we will almost be sure to introduce bugs. So one classical change is to swap the first two lines in the scan function, so that we don't set X to true first, but we rather initialize the B array first, and then we set X to true. And that should result in this one, which is almost identical, but it should be buggy, right? It probably is buggy. It should be buggy, according to literature. So let's test these algorithms. So how do we do it? We execute around 1,000 concurrent calls to scanner write, okay? And the results are, with the stateful tool, the result is that Gianti's algorithm works. This is fine, no bug was found. But his buggy variant works too. We didn't find a bug there, so that's really bad, that's really depressing. What did we do? Well, maybe we have a tool that always says true. It could be the case, okay? So what is wrong? If you started looking at that, this is a classical problem that in some sense the state space of this program is not too small, and the timing has to be pretty precise to actually find the bug. It's not so easy to find this bug, okay? And in practice, the Erlang scheduler is just too deterministic. It makes deterministic choices that are not conducive to finding this bug, except in very strange circumstances. If you are lucky or if you are unlucky, maybe you can find it, okay? So what is the solution? Let's try to make the scheduler more random. And again, this is not a new idea. It has been around for a long time, and John has also worked on that. But let me explain what we do. So this is our naive algorithm. So what does it mean to randomize the scheduler for this example? So what should we do? In some sense, what we should do is to not commit to choices until as late as we can, right? So what are the choices? What are the effects that affect the behavior of other processes? Well, in this this naive example, there's just two things we do. We either write to the key value store, we get from the key value store. And those are interacting actions, right? So we should somehow be careful how we execute the put and get, okay? And how do we do that in practice? Well, again, we have a library to do that. It's publicly available on GitLab. And it instruments the code to be able to, in the following way, right? So the idea is calls in conflicting APIs. So this is the KV API, or this uses the KV API, and the calls are put and get. So before making a call to put and get, the idea is that the program doing that should ask for permission to do that. So who answers this request to the permission? It's a scheduler process that works, again, runs separately from the other processes. So the protocol is as follows. The scheduler process starts waiting, and if there is no permission request, it just waits until the first one comes in, okay? And when the first request comes in, so somebody wants to execute, for instance, KV put, well, it continues waiting for a little bit of time to see if there's more requests coming in soon, okay? And then, after having waited this small amount of time, it chooses randomly which permission request to grant, and then continues with step one again. So it's a very, very, very simple, simplistic idea. And there's more stuff to do if you want to, for instance, cover message path communication in Erlang, but this sort of works for this really simple case. And it's very easy to instrument, again, the calls to KV get, KV write, using the Elixir macro facility. Okay, so we have done that. Okay, no big news. So if we run this naive example that we saw before, apart from just executing the example, what else comes out? We get an execution trace explaining behavior of the naive snapshot, what really went wrong. So this is the structure you see here, which is a list of decisions taken, permission requests granted by the scheduler process. Okay, so each line is one request, corresponds to one request permitted. So there's a tuple of two components. The left one is the request that was granted. So the first one, the process Q, asked to execute KV get, and the left and the right component are the requests that were possible to grant at this point in time, but which were delayed. Okay. So P also asked to execute KV put, but it wasn't allowed to. Okay. So this is the basic object that comes back from an execution, running a program under the scheduler, okay? And of course, we can do the classical stuff. This is a repeatable, if you will, some kind of schedule that we can repeat, that we can run again if we want to. We can also examine it to see, well, what were really the intricate steps that caused this bug to appear, okay? So that's good news. We can check the Giantis algorithm using the random scheduler, and in the correct version we didn't find any bugs, and the incorrect version, yeah, we find a bug after some time. So this is again a time diagram showing more or less the number of operations that were necessary to come up with the bug, find the bug, and the detailed execution trace produced by the scheduler for this example, I think it has around 30 scheduling decisions. Okay? So it is helpful to find out. You could think of using a debugger to step through the program and finding out exactly why it behaved as it did. Okay? So that's really useful. But it's not very new, right? So this was in some sense available already in the Pulse tool produced by QWeek, okay, in QWeek check. What is new? So my background is in model checking, right? So when I see something like that, I start thinking, oh, yeah, that's good, but can we also do some model checking around that, right? So if we have a really small toy example, and you know that people in academia like toy example, I like the toy example, can we be sure that we find all the possible errors, right? So what we can do, we can play a game of manipulating these execution traces a little bit to find all possible behaviors. That's the idea, right? And for a simple program, for a toy example, we can find all possible schedules or all possible ways of executing the program. For a more complex program, we cannot hope to do that for a realistic program, but maybe we can hope to at least always be innovative, to always explore new behaviors and never repeat schedulings that we have seen before. So that's the hope, okay? So how do we do that? Well, exploring all schedules, that's a classical, really classical depth-first exploration, for those of that's familiar with this term. So the basic idea is we just run the program once. Well, we have run the naive example here once. We get back this execution trace full of detail. And now we want to continue, right? We want to vary this behavior. We want to find new behavior. How do we do that? Well, this is step first. So we're going to start with exploring the first choice point, the first alternative that wasn't explored before. And in this case, the first alternative is on the third line here. Essentially, this here, where the queue process wanted to, the latest choice point, that the queue process wanted to read from the array in this end. Wow. But it didn't happen, because instead the P process executed. So in the next schedule, to try out, we just instead use the queue option. And this, of course, this scheduler tool has the possibility to run schedules like that. So we just run it. Out comes another execution trace. And we can repeat this process, right? Finding out all behaviors. And when we finally finish with this example, with this schedule, well, we go back to the previous one choice point that was there, the earlier one, the second one, right? And continue with that. And eventually we'll exhaust the full behavior of the program. Okay? It's a really simple idea, but it's one way of doing model checking around this, this idea. Okay? So why is this interesting? Well, model checking has its problems. I've worked with it. You have to record the state, and you have to go back and things like that. Just executing schedules like that is a nice idea in some sense. Okay? So what are the drawbacks? Well, this is good, right? This is efficient. If the program is small enough, we can do everything, right? But suppose the number of schedules possible is really huge. A realistic program. Well, what can happen? If we are unlucky, the bug in the program happens because we make a really bad initial choice in the program. So the first thing we do is, well, going left instead of going right, and then it fails. And if we're unlucky, we just always try going right. So we never find the bug. Okay? And if the number of schedules is huge, we are never going to explore this initial decision again. Oof, that's bad. Okay? So really, ideally, we would like to be more random also with the next schedule that we're going to explore. And that's the idea for the second algorithm, the controlled random exploration algorithm. Okay? So this is also a simple idea. The algorithm runs as follows. As began, we always begin by just running the program once, obtaining a trace. Okay? Next, we generate from this trace. Remember, a trace has a lot of choice points here, right? All of these ones are possibilities that we didn't explore. So we generate from this one all the schedules that correspond to taking one of the choice points. So here we have 3 additional choice points, so this would make 3 schedules for this example that we have to explore. So we generate them, we store them in a data structure, okay? And then randomly we pick one element from the data structure. This is one schedule. It could be the first one, it could be the last one, we don't know. We do it randomly. And we run this new schedule, and we get back a new set of schedules, and we repeat the process until either we explore the whole behavior of the program as possible, or we run out of time because we don't want to test more. Okay. So what are the drawbacks of this one? Well, the algorithm uses much more memory than the depth-first exploration. And its runtime efficiency depends on these operations that we do on the data structure. How good is the data structure, right? We are storing schedules. We are looking for, we are we are deleting them, we are doing a random, extracting a random schedule for the data structure. So with a decent data structure, we can do it decently. So in the prototype, the scheduler implementation, we use balance tree implementation. That's the GB tree implementation. That's available in the Erlang standard library, which is pretty okay. All operations have logarithmic complexity, and at least these ones. So it's pretty okay in practice. And in practice, so we tried quite a lot of these snapshot algorithms using this one, and it seems to be pretty good at finding real bugs, but there are no firm performance data yet. Okay? So how do you do? If you want to do this, just as a last slide, what is needed to use this tool? Well, it's not so much. Here you have a little bit more stylized, the main implementation. The only thing that one really needs to do is this line here, use scheduler, with an option module saying that, well, you should control of all functions executed in the KD module. So they should be always under permission. And secondly, we also have a parameter here that's integrated with the linearization checking, saying that we also want to do linearization checking. This entails for each of these three functions to inform when the function is called and when it ends. Okay? So this is the sort of visible user interface to the tool. Okay? So that's all I want to say today. I'm part of a large research group at UPM, and we do quite a lot of tools around model checking, about property-based testing and things like that. So runtime contract checking. So check out these links if you're interested and contact us. Okay, thank you.
Have any questions?
Yep. So that was very interesting. One question is, you've used the answers from the first run as the oracle for what the answers should be, but there are APIs that are designed to return different values every time, like now, for example.
Yeah.
Have you got a story on those?
So this was a simplified presentation. We also have a possibility of mixing in a model, right? As you so specify, and this sometimes can be more efficient as well because you can cut down on the linearization, right? So we do have the possibility of mixing in a model, okay? But if you don't want to specify a model, well, this is somehow okay as well. So it depends.
Right. So the other question that I wanted to ask was that when we've used timestamps, I think we've recorded a timestamp before a call, and we've discovered that they're often inaccurate because processes suspend between recording the timestamp and making the call. You're using timestamps to cut down on the number of schedules that you need to consider. Do you finesse that problem by taking a timestamp before and after? Or?
We do take timestamps before and after. So for this example, for instance, we take when we write, we take a timestamp here when it starts to run and one afterwards. And we try to optimize it a little bit further so that if we do both the scheduling instrumentation and the linearization instrumentation, we can actually try to move it to the closest point where the scheduled action takes place. So in some sense we say, oh, actually this default write doesn't start until we actually execute the period part. But timestamps are pretty okay nowadays. They are monotonic as it's guaranteed. They can be the same, so they don't always increase, right? They can be the same, but they also should be consistent for different processes. And we haven't seen any practical problems.
I guess by having a timestamp before and after, then if the timestamps are separated in time from the call, you just assume that they might run in either order, so you just explore a little bit more.
If there are two intervals that doesn't overlap, then there is a precedence. That's guaranteed. The problem is that if one ends and starts at the same time, then we cannot say anything, right? Because the way timestamp works. But the hope is that we can cut down a lot, and we can cut down a lot of the the problems with having an explosion of orderings in this way. Okay.
Do we have any more questions? Comments? Okay, so thank you.